So I'm here to talk about the RabbitMQFMU, which maybe solves the problem that was asked by Jose earlier on. So I'm just going to briefly tell you what the connection for RabbitMQFMU is to digital twins, going to give you a brief example, discuss the approach a bit, and then give you some details on how it actually works. So the idea is that you have some sort of deployed system and it continuously logs to a system log. Now you want to run a co-simulation or a digital twin in coordination with this deployed system. So you have some sort of entity picking it up and sending it to a message middleware node. This could be a RabbitMQ server. You then have the RabbitMQFMU running in your co-simulation over here, and it basically receives the messages or consumes the messages put here and makes it available to the FMI co-simulation. So this way you can sort of bridge the gap between the real world and the co-simulation world. So I'm going to give you a very brief example with the classical water tank that Hugo also showed, except that here we only have one water tank. You would like the water to be between these two. You have a controller, discrete event controller, you have a continuous time system. So I actually ran this case in an internal workshop in January, and the issue was that you could see that the orange line is the FMU, and the blue line was supposed to be the same as the orange line, but it was not. And this was due to some imprecision of real numbers, which I will get back to. So the example is that we have outputs from a previous co-simulation of the water tank, as I just showed you in the figure. We have a publish script that just publishes these values to the RabbitMQ server. These then comes into the RabbitMQFMU. You have an FMU that calculates the difference between the outputs of the RabbitMQFMU and the actual co-simulation of the water tank and the water tank controller. So all of this is available in an example online, and you also have a Docker image for the RabbitMQ server, and you have the Python script to publish data, and you actually have the data. So it should be good to go to try it out. Good. So here is a brief example of it in the Into CPS application. So as you can see, I have set up the example in Into CPS application. This is what the example on GitHub looks like. And here, if we look into the parameters of the RabbitMQ, you can see there is a precision parameter exactly related to the issue that I just showed you with the imprecision of real numbers. So if you try to co-simulate it, you can see that there is no blue line, the RabbitMQ line, is because it is exactly beneath the orange line. So the precision, setting the precision to 10 solves it in this case. And all of these things are documented in the online user manual that I will give you a link to later on. So there you can see the blue line is just behind it. Good. So the approach that we did was that we sort of modeled our approach in TLA+, and then we used the TLAC model checker to check that it actually executed as we desired. So here is sort of what it looks like, where we have an FMU state and we have an environment state, where the environment is representing what is available on the server. I'm not going to go into details on this. It is available online. So what we also did was that we implemented the RabbitMQFMU in parallel because we needed an implementation early on. And the way we test the implementation is that we generate test cases while the TLC model checker is actually running them. And then we apply these to RabbitMQFMU tester. So yesterday we executed 32,000 tests, and some of them were skipped due to internal no-op operations within the model checker, but 22 of them successfully completed. And so far, no failures. So initialization is that if you have a RabbitMQFMU that would like to receive or would like to output 5 different variables, then we need to block and enter initialization mode because these outputs have to be available to the other FMUs. So what we do is that we receive all 5 messages, or we block until we receive them, and we use the latest timestamp of these outputs to define the actual output that creates an offset between the wall clock time and the simulation time. In do step, we read the messages, we extract the offset to get the simulation time, and this was the offset that was calculated in initialization. And then we set a message as a given output if it's less than the stepping 2 time, but it's newer than the current output. Or we can keep it for later if it's a future value. So the configuration, we have these parameters. I'm not going to go into details with these because it's also available in the user manual. But the precision one I mentioned, it's basically the number of decimals to consider in the communication step size and current communication time after you have converted to milliseconds. So this is the data received from the orchestration engine, but these are just real numbers and they can be imprecise. So this is why we need this. So max age, it's a parameter stating how old a message is allowed to be. And then look ahead is a measure of how many messages which you retrieve from the server on each processing. So if we look at how to represent an output from this RabbitMQFMU, then what we do is that we actually pass the model description file within the FMU, so we can look for this level, the name property of a scalar variable in the messages that are sent to the RabbitMQFMU. So basically, you only have to write the model description file. You don't have to do any other configuration for this. So the level here matches a JSON message level parameter here. Good. So basically, it has been very difficult to implement this while doing the model because we need lots of communication between the model developer and the FMU developer. And the coronavirus made this issue a bit of a struggle. So we've spent quite some time on mapping the data representation of the FMU and the data representation of the implementation. So this is just interesting in terms of the approach. But I think the best approach of the model checker testing approach has been the discussion on the semantics. And that was basically because we found that it was implemented one way in the implementation and another way in the TLA Plus model. So it's very interesting to see these two views on implementation, and sometimes one was correct, other times the other one's correct, so we could sort of fix one with the other and vice versa. So down below here you will find some links where you can find the FMU, the TLA Plus model and the test case generator, the example that I showed you, but also the documentation. So I hope that everything you need to use this is there, and it's ready to be used. We would love feedback. It has not been used in actual studies yet, so please go ahead and use it. And that was it for me. Oh, sorry. So the future work finished documentation. I actually finished it last night, so that's good. We need to execute all the tests from the model checker. I was just generating while we were talking here, and we have 1.8 million tests that we have to run now. So there's some work there. Then we need to send data the other way around from the co-simulation to the real system, and that will be in a later update. But it should be a more simple approach. And then after the summer vacation, we will start to build a digital twin case study where we'll use this for actually bridging the gap between the two worlds. That was it. Thank you.
Thanks, Casper. Any immediate questions for the last couple of presentations before I say a few concluding remarks? Jan, you have a question here about the data pathway. Yeah, okay. That's planned to go both ways, yes.